All right, well, thank you for everybody who came today. It's a pleasure to tell you about what we are doing, or what I also have been doing. So it's a big title, and I will tell you a bit about, of course, the story, what I've been doing. Here's a bit who I am. So I'm initially from Munich. So I graduated from the Technical University of Munich. Then I worked for quite a while on the so-called ice cube experiment, which I will tell you about quite a bit, because it's an exciting experiment. It's at the South Pole. It really captures a little bit by its location itself the imagination of people. Then I joined the ATLAS experiment, which I will not talk so much about. I will give a bit of a comparison, because of course particle physics can always give nice comparisons. And then I joined, let's say recently, three and a bit years ago, SFU as a faculty. And from there, I sort of coming back to neutrino physics. And this is the story a little bit I'm going to tell you. Especially talking about sort of ice cube, I also never really thought how much excitement you can have as a particle physicist. So this happened early this year, actually. So people found the Endurance. I don't know if people ever heard of the Endurance, but that's Shackleton's ship, which he essentially sailed into the Antarctic. And it got stuck in the ice, which you can see on the left. Then it sank. Most of them got rescued. It's quite an epic story. But ultimately, the ship was lost, and recently they found it. So it's quite nice and exciting. And once you've been in Antarctica, you always feel somewhat attached and want to relive certain stories. So I tell you this as well because I also had my own cruise. So what you can do as a particle physicist, we have essentially on IceCube a surface array detector, which I will not talk about at all really during this talk. But we try to calibrate this. So we put it on a container on this ship here. It's an icebreaker. We started in Sweden. We crossed more or less the Earth down to Antarctica, circled around Antarctica, and came back. And I had the pleasure to babysit this experiment during that time. So it was a quite exciting thing. Things you don't expect or imagine to do when you do your PhD as a particle physicist, that you actually can become a sailor. I had also no idea. It literally came up in a meeting. Who wants to babysit this thing? I said, yes, I'm do this. I go along. So it was quite exciting. All right. So this is basically what I do a lot now as well. This is some images from the Large Hadron Collider and the ATLAS experiment. And then, of course, this is what I will talk about in this talk as well, that we are trying to build a neutrino telescope, maybe possibly here, and why this could be quite exciting here in BC. OK, back to the talk. So I hope you take a few things away from this lecture today. So one is I want to tell you what is a neutrino. Then why are neutrinos special? And I only tell you one aspect why neutrinos are special. They're actually very, very special. But I'll tell you the link to kind of astrophysics, astronomy, and what you can do with that. The neutrino itself is also very interesting to study, but I will not talk about this today. I will hope I can convince you how we can detect them, at least the ones which have a lot of energy. And then the last part is why do we want to detect them in BC, which is, of course, very exciting for us. OK, so if we look at our everyday world, I'm sure you're quite aware of that we have the atoms. The atoms are our building blocks, and they're made out of protons, neutrons, and then whatever picture you want to paint, the electrons somehow swirl around this. And this is literally the building blocks of everything we know. So this is, you can build all our structures, you can build all organisms, human beings, everything out of this. But of course, we know that it's not the end of the story. So we know that the universe is made out of more than just protons, neutrons, and electrons. Of course, if you know a bit more about particle physics, then we also learned that protons and neutrons are not by themselves the elementary particle, but we can take them here as the building blocks. So we can essentially ask ourselves what's wrong with this picture. So this is the most basic nuclear reaction we can think of. So a neutron is a little bit heavier than the proton. So the neutron can decay into a proton and an electron. But you also see these are the building blocks of an atom. So if this would be the whole picture, more or less what would happen is that electrons and protons could just combine back and create neutrons. Or the neutron goes back into a proton electron. So we wouldn't get stable matter because everything just could go back and forth. We know this is not what's happening. So at the same time, when people studied in the 1930s the decay of neutrons, so you can wait around 9 minutes till it decays roughly, into a proton and electron, they could measure the mass of because they're charged particles. You can measure the mass of the electron and the proton, and you can measure their velocity. So then what you can do, you can calculate their momentum, which is the mass times the velocity. And then we have one of the fundamental principles in physics, which is that momentum has to be conserved. So when this neutron decays, you have to conserve the overall momentum of this decay. And what they observed is that indeed it was not conserved. So what was proposed in order to rescue particle physics at that time was that there should be another particle which is flying out. And this was when the neutrino was born. At that point, they had no chance to detect this particle. It had to be neutral. It had to be quite light. We actually still today don't know its mass. And it is called neutrino because Pauli essentially postulated the little neutral one, which is neutrino, and said at that time he has done something very terrible because in order to rescue the theory, he proposed a particle which we can never detect. Luckily, by now, we have actually detected them. So already in the 60s and so on, we knew neutrinos exist. So by now, there's no question that they exist. But they're still extremely interesting particles to study and also use as a messenger. The thing is now, of course, we know we have more than protons, neutrons, and electrons in the universe. But it's quite amazing when you think about the numbers. So for every proton, neutron, or electron in the universe, we have billions of neutrinos flying around. So the number is enormous. So the things we know, which makes everything we know, is a real rarity in the universe. And neutrinos are something which is much more abundant. So where do we get them from? And this is also quite interesting. So all of these, what you see, the images, they produce neutrinos. The important thing is what you see, they trace some form of nuclear reaction every time. So you can ask yourself, why is our body, where we can see it's on the order of millions, like hundreds of millions neutrinos a day, which we emit. So where does this come from? And this comes essentially from decays of potassium-40. So if you want to increase your flux of neutrino, you want to be a high neutrino source, you eat a lot of bananas, you get a lot of potassium, and then you will shine very bright in neutrinos the rest of the day today. So you can do that. Obviously, the neutrinos, nuclear reactions, so a nuclear reactor will emit a lot of neutrinos. The Earth has a lot of nuclear reactions, so this is a huge source of neutrinos. We can get neutrinos from the Big Bang. These are also very special and very interesting to studies. Now we come to the part what the remainder of the talk is quite interesting, so I'm very interested about is neutrinos which are created in explosion of stars or in astrophysical phenomena, things we want to understand better. Of course, the sun is one of our brightest sources in neutrinos, so they emit 100 trillion of neutrinos per second. A huge amount of energy is released in these neutrinos as well. And then also we managed to create neutrinos in the lab, so-called neutrino beams, and I will show you a bit that this is actually more the analogy. What we can do on Earth is exactly the same what the universe does, just much better. So all of these things are really, really interesting, and they have the common denominator, so to speak, that everything where neutrinos are emitted from trace nuclear reactions. So if you can detect neutrinos, you can understand something about that source. You can understand what is going on inside, because directly in these nuclear reactions, the neutrinos are created, and they will tell you something about, like they are literally the messenger of this reaction, if we are able to detect them. So an analogy why we are interested in astrophysics to look at this. So if you injure your hand, let's say you fall, you think you broke something in your hand, a bone, or you hurt it in a different way, obviously we can look at it visibly. Sometimes you see a bruising, sometimes even hopefully not the bone sticks out, so you can learn something. But luckily, every time medicine made an advancement, we found something new, like, for example, X-ray or MRI here, or also infrared is probably where we look the least at our hand, but this is what we could see where the blood vessels are predominantly. So where the heat is in your hand, where the blood vessels are directly close to the surface. But every time you look, you will learn something new, or the doctor will tell you something new. You broke your bones, you tore some ligaments. So whenever you have a different means to look at an object, so in this case it would be 4, visibly, or now kind of 3 ways to look inside your hand, you will learn something new, in this case about your injury. So we want to do exactly the same. So if we take, for example, the Crab Nebula as an example, it's one of, would have been fantastic to be there in around 1,000 years ago when this exploded. So it was very bright. It was like a second sun for a while on the sky. So it would have been amazing if something like this would happen again. We can do the same in astronomy or astroparticle physics. So we can try to look. So everything you see here is essentially is the electromagnetic spectrum. So photons at different energies. So we look at them at radio. So this is the lowest energy up to the very highest energies. These are the highest energy photons which can be emitted and which we can detect. So every time you look at this Crab Nebula, you learn something else. So in radio and infrared, you can see kind of these filament structures, and you see areas where you have secondary emissions because there are lots of magnetic fields, and the atoms, essentially, they are excited and they can emit photons in these regions. You see sort of the remnants of matter in the visible light. Then probably if we skip ultraviolet, you start to see emerging a core. But then X-rays is very interesting. When you look into X-rays, you actually start to see something completely different. And you see the neutron star emerging, which is right in the middle. And you can kind of imagine an accretion disk here, where all the matter is kind of rotating. It's falling into this neutron star. And this neutron star is kind of creating certain jets where it emits material. So if you look online, there is actually some sort of images, GIF images, which you can see really this happening. And now when you look to the gamma rays, the highest energy of all of them, you can essentially see nothing else anymore than the bright neutron star, which is just emitting gamma rays. So you only see the source, which is left over. If you wouldn't have these tools, you wouldn't even know what's at the source. You would just, okay, maybe everything exploded, nothing is left over here. So every time we looked in a different wavelength, we learned something new about the objects, about the universe, and of course also how they explode. So now the question is, we want to understand how does this look in neutrinos. Are there neutrinos even emitted? And then if the neutrinos are emitted, what can we learn about the source? As we said, there are traces of nuclear reactions. So somewhat, if we get neutrinos, nuclear reactions have to be happening inside these sources. So coming back to how can we actually get them, so what we can do on Earth and what the universe does is exactly the same. So if you maybe have ever been at Triumph, you can accelerate protons to rather high energies, in cyclic and like in such a synchrotron or accelerator here, whatever you want to build. Then you can dump the proton beam into a target. When you have this, you have nuclear reactions, and eventually the charged particles you can deflect out, and anything which is left is in the decay here. If you put a lot of material in between here, is a neutrino beam which would come out. So this is how we would create a neutrino beam in the lab and how neutrino beams are created. The universe does exactly the same, just has significantly more powerful accelerators. For example, you can replace the cyclotron at Triumph with a supermassive black hole, which has a little bit more energy, has a significantly higher magnetic fields. So you can accelerate charged particles to enormous energies, and you kind of experiment where you target, where you dump these accelerated particles in, is just nearby radiation. Nebulas, remnants of material which is flying around, and this is your material, you dump your beam of charged particles in. The result is exactly the same. You get nuclear reactions, eventually you get pions, you don't have to worry about pions so much, and if you have charged pions, you will get neutrinos. So the universe does exactly the same as an accelerator on Earth does, just significantly more efficiently and at higher energies. So I want to draw the comparison. That's the only thing I have about the Large Hadron Collider. Probably many of you who are interested in science have heard about that. I obviously work with that as well. So this is an image. Obviously, you don't see the ring of how large the Large Hadron Collider really is. So it's 27 kilometers in circumference, and it's located near Geneva. So this is the main storage ring. And we have around this 4 main experiments. So Atlas and CMS, and 2 further on experiments. So I work also with the Atlas experiment here. So it's the most powerful accelerator we have on Earth. Yeah.
So basically from here, why does it seem like it's just multiple particle accelerators in what?
You mean here, in this one?
Yeah, like those.
Yeah, it's a good question. So we cannot just start from here. So you start with a small particle accelerator to get it up to a little bit of energy. Then you put it in the next one to bring it up to more energy. And eventually you put it in the big ring where you finish it off and get it to the maximum energy we can achieve.
Also, how much did this cost?
How much it costs?
Yeah, this thing.
It's a very expensive experiment. Let's put it there. All right. So what I want to draw in the comparison is, so you can say, okay, great, why don't we just make it in the lab? Lab is always more controlled. We can study everything in the lab, usually in a much better environment than what the universe can do, because we don't know when it does it. It's far away. It's hard to understand. So if we would keep the same technology, let's mean the magnets. So the magnets are bending the charged particles. That's actually what's driving the size of the Large Hadron Collider. If we could build stronger magnets, we could make or create higher energetic beams, let's say, simply said. So if these are the top of the line and we want to achieve the energies the universe by itself can create, we would have to build an accelerator, which is the orbit of the Mercury. So it's huge. This is the comparison, what the universe can do versus what we can achieve these days in a man-made machine on Earth. So it's ginormous. Okay, so this only tells us, great, we can get neutrinos, but why is the neutrino so interesting for us to look at? And this is why, because it is a fantastic messenger. So we have 3 messengers we can use as to study the universe. One is, why don't we just use the charged particles, like a proton here, directly? They are created, why don't you just study these? The problem is we have lots of magnetic fields in between the creation of these particles and where the Earth is. So charged particles are deflected by magnetic fields. You never know where they are. You can't map them. So when you detect charged particles on Earth, you know their energy. They're very high in energy, so you know they exist, these high energy particles, but we have no idea where they came from. At the same time, photons, obviously, this is what we always study the universe in, photons. They're fantastic, but photons also don't tell you the true story, because when they're emitted, they usually pass through various layers of material. They can get absorbed. They can get what we call shifted in energy. So photons also generally don't tell you the full story if you can detect them. So the neutrino is beautiful because it just is emitted, and because it is so hard to detect, it just comes to you, it doesn't change, and we can hopefully detect it at Earth. And it is the ideal messenger because it is electrically neutral, so magnetic fields can't deviate it. It's essentially massless, has a tiny mass. It's essentially unabsorbed. It tracks nuclear processes, so exactly what we want to learn about the object itself. But all these things which make it the perfect messenger make it also very hard to detect, because otherwise you would have too much good things of all worlds. Okay, so this is a bit of a complicated plot, but this is a motivation why we really also want to study this, and why maybe things are out there which we have never even been able to see. So what you see here is energy. I'll have the same scale later on, and you will see where the LHC sits. So this is a lot of energy here, the highest energy phenomena we have, to very little energy down here. You can see this is a distance scale. So the further away you go, these are really far away. So here we are at the galactic center. This would be the distance to our nearest galaxy, nearest so-called blazars, or if you go further, you go to cosmological distances, so really, really, really far into the universe. The energy roughly up here corresponds to how we can sample or understand the universe. So these are photons, so the cosmic microwave background is the lowest energetic photons we generally can observe. Here's the optical, then we come to what you've seen before in this image of the Crab Nebula, X-ray, gamma rays, and then up here would be neutrinos and cosmic rays in terms of their energy. So what you see in black here is around 20% of the universe in energy and distance, which we're absolutely blind to because the messenger can't get to us. So the photons get absorbed, the charged particles get deviated. So there's around 20% of the most highest energy universe, which we have no idea how it could look like. Like, we really have no idea. And that's where the neutrinos come in, and the neutrino could reveal what is happening in these regions. So the furthest away and also the highest in energy. Of course, you can see also the ripples down there, which should be gravitational waves. So this is another very interesting tool to understand, for example, neutrinos and gravitational waves together. Okay, so if you want to detect them, you have a wish list here. So you should have a very large target mass. Water is good. So build something very big to detect them. provide a very clear medium because we need to detect something. So what we needed our source is light. We'll show you in a second how. And then be at least somewhat shielded from external events like cosmic rays. And this is usually how you can do that. You go deep underground. So you try to go somehow deep. For example, deep in the ocean, or as IceCube did, deep in the Antarctic ice sheet. So how do we detect in these detectors the principle for a neutrino? So a neutrino would come in somewhere, let's say about IceCube, we have now ice, would make an interaction with a proton in the ice, or a nucleus in the ice. In this interaction, you get a muon. A muon is nothing else than a cousin, or basically a brother. It's just heavier of the electron, has the very similar properties than an electron. It's just heavier. So this muon is created, and it has so much energy that it can travel for hundreds of meters or kilometers through the ice. When it does that, it emits something very characteristic because it is traveling faster than the speed of light in that medium, so not absolute speed of light, but in that medium. And then it emits something very characteristic, which we call Cherenkov emission. And you can have an analogy of this, which is a sonic boom, or essentially an aircraft which is flying supersonic. So you also will hear that aircraft, the shock wave reaching you in a very characteristic cone-like structure. So if basically you hear the little images of an aircraft being stopped, and then when it starts to accelerate, come to the sound barrier, speed of sound barrier, and break through it. And the same effect, or a very analogous effect, is happening with these charged particles traveling more or less supersonic through the ice. And the light emitted here, we simply detect with very sensitive photodetectors in the ice. And we deploy them in a kind of a lattice grid, and we try to pick up this light. From the sensors here, you get your signals, and you can reconstruct the path of this muon. And from this, you can infer the initial direction and energy of this neutrino. So you never see the neutrino itself. You only see what comes out of the reaction of the neutrino in the ice. But at these very, very high energies, you can really extremely well infer the direction and energy of this neutrino, which is created. All right, so let's talk a bit about IceCube. IceCube is located at the South Pole. It's a humongous detector. It's the largest neutrino telescope we have currently on Earth. So here you see the footprint. It's a cubic kilometer of ice, and it's deep in the Antarctic ice sheet. So it's around 3 kilometer deep under ice, so 2.5 kilometer deep under ice. So here's the geographical South Pole and the South Pole Station, and roughly a kilometer away from it, and you can see where this is the central IceCube counting house. So how do we build IceCube? As a little video. So first of all, we have to drill into the ice. So we do this first with it's kind of a hot, just you simply melt the first few layers because the ice is actually not very dense in the first 50 meters. After that, we use a different technique, which essentially you spray super high-powered hot water spray nozzle, and you start to melt the ice, and you melt these kind of holes for up to 2.5 kilometers deep. So it's a huge endeavor to bring this to the South Pole. So this is the power plant which allows you to create the hot water and the energy needed to actually drill these holes. You can drill, as you can see, a speed of around a few centimeters per second, so it takes around 2 days to drill these holes. Here you can see how the drill rig is moved on the South Pole. This is the hose. It's a massive pressure hose. And here you see a few images now of steaming images of the tanks, how the hot water is created. So you essentially dump with a bulldozer snow into these shipping containers. They get heated up. The hot water gets put under pressure and put into the pipe or in this hose. And here you can see the image of this drill bit or this drill hose being pulled out. And after the hole is drilled, you have maybe around 48 hours to deploy your detector. Otherwise, it starts to refreeze from the top. So it starts to refreeze from the top and then freezes down. And it takes actually some months to freeze at the very bottom due to the pressure. So these are now your optical modules, which you bring. This is where the scientists arrive. So these are these very sensitive cameras with their electronics. And we essentially attach them to a cable, which gives us power and the way to read them out. And then they go down on their journey into the ice and eventually are frozen in there. So you see, these are probably 15, 20 meters, where the water is actually, the ice is not dense enough to hold the water, and only then you get to the water. So this is how we built it. And essentially you end up with a, here we go, a three-dimensional grid. So this is now each of these long cables. So we have 86 of them in IceCube. And there are little blobs on there, which are these optical sensors. And here you can see an image of how we actually can reconstruct such a muon track. So it comes through, and by the time when the photons arrive and the amount of the photons, which gives you kind of the size of the colorful blobs here, you can nicely reconstruct with high accuracy the tracks of these particles going through. So this is how IceCube can determine their particles, or the muons in that case. All right, so what have we actually learned from IceCube, and why do we think it's exciting? So maybe some have heard, so in the last 2 weeks, IceCube presented new results, had some sort of public announcement because they found very nice new results. So it's a good time to also give this talk. So one of the things, this is a very complicated sciencey plot, but it shows something very, very interesting. So first of all, I wanted to show you, here is now the same energy axis we had roughly before. So this is where the LHC beam energy is. So you can see you can go quite a bit higher in the universe in terms of energy, significantly higher. What you also see, the different messengers. So these are photons, this would be neutrinos, and these are our charged particles, the protons. So they obviously reside at different energies, but the interesting thing here is that the y-axis here is a complicated unit, and it's a proxy for energy density, or in other words, it's the amount of energy that reach us from the universe per second. So every second, this is the amount of energy the universe sends us in each of these messengers. And one very interesting thing you see, they're all equal. So we see a lot of photons, we need a lot of charged particles, but what you see is that the same amount of energy is sent by us every second in neutrinos. They're just very, very hard to detect. So the neutrino universe is extremely energetic. So it is really interesting to study. You can also see already by something we call error bars that we have detected so far very few neutrinos. So we would like to detect significantly more neutrinos compared to the high precision you can see in the other messengers. The other thing is, of course, we want to understand sources, and IceCube so far has seen two sources. The kind of holy grail is to understand, to see of an like one of these astrophysical phenomena, a neutrino, and at the same time you have also, for example, with gamma rays or other messengers, a coincident observation. So here you see an image of a blazar, which is a supermassive black hole, which has this typical accretion disk around it, and then it emits these super high-powered jets, which you can see here. So this is exactly what has happened. So here are some IceCube high-energy alerts. I will actually skip this because I'm taking a little bit too much time. But essentially what they have seen is we detected two very high-energy neutrinos. In principle, very fortunate because we were staring down exactly the gun barrel of this blazar. So this blazar was pointing at Earth directly. So we could detect neutrinos, and at the same time several satellites and ground-based photon detectors, at very high energy photon detectors, have detected exactly at the same time a very unusual flaring state of this source. So this is what you can see here in sort of location in the sky. And you can see the color map underneath here is the photon counts, very high energy photon counts, and the little squares are the neutrinos which were detected. So this is a coincident detection of neutrinos and high energy gamma rays for the first time. So the first time you can actually pinpoint a source in the sky, but it's one neutrino or two neutrinos, so very little. But it is significant enough because it happened in a very short time window. The other thing is what was presented very recently is a second source. So this would be how IceCube can search for, so you get lots of these neutrino events, and you wait a long time, and eventually you see, do they cluster somewhere in the sky? Do we get a hotspot of cluster? So essentially this is exactly where this NGC, this galaxy here, is pointing to. So this emerged as a cluster of lots of neutrinos come from the same location, and this is an obscured black hole. It's a very different class of phenomena. So you have a massive black hole which is obscured by a lot of matter around it. So you actually get very little photons from this object in the universe. But you did get a lot of neutrinos. So this is IceCube's second source of neutrinos. So when we look at this, why do we actually want another neutrino telescope? And you look at the timeline. So IceCube was started to be built around 2000, the early 2000s. It was completed in 2011. It's taking more than 10 years of data, and we've seen 2 sources now. It's a fantastic experiment. It's really great. It's just on the threshold a discovery machine. So it tells you it's out there. The neutrinos are out there. We can get the science, but you need to make it a little bit bigger. Otherwise, you wait a very, very long time for each of the neutrinos. So if we look at how many neutrino telescopes do we have on Earth, the only one which is of that size is IceCube. There are a few other ones who try to grow and become bigger. So one is in Russia, in a lake. One is called Cubic Kilometer Net, which is in the Mediterranean in Europe. And the new kid on the block, of course I had to make it the highest, is what we are trying to do is the Pacific Ocean Neutrino Experiment at Ocean Networks Canada. But we are also the youngest. So these are significantly more advanced, but still nowhere at the size of IceCube at the moment. So obviously you saw the other ones, they're not in the ice. So the question is, can you go also fishing for neutrinos? So can you change the ice to water? And yes, you can do that. It has different challenges. So why are we interested here, right in BC? And this is exactly the reason. This is because of Ocean Networks Canada. I also didn't know about this before. So it's one of the world's largest and most advanced cabled ocean observatories we have on our doorstep here. So Canada has invested a lot of funds and time into this network, and it's, of course, dedicated to climate change studies, oceanography, marine biology, so very different topics than physics. But of course, for a neutrino telescope, you have to go deep. So you can see this is almost 3 kilometers deep, the Cascadia Basin. You need to have somehow power data transfer in the ocean, and a group who actually knows how to connect sensitive devices and power them down here. So in principle, this is a fantastic group to work with because they know exactly what they're doing. And you don't have to build this infrastructure in order to build a neutrino telescope here. It already exists. So in principle, we have to build our detectors, and there are specialists who can help us to deploy them and connect them. So that is the reason why we're interested here in BC and not, for example, on the East Coast or in the US or somewhere else. It's the opportunistic part that Ocean Networks Canada has this infrastructure here. So what have we done? We have in 2018 and 2020, we looked at it and saw, can we actually do this there? Because you can imagine the optical properties of the ice and the water are quite crucial. If it's simply, so you need to be able to have a quite clear and transparent environment. It has to be quiet. Oceans give you different issues. You can have lots of biomatter. You can have lots of organisms floating around. So you need to understand, is the water actually suitable to build a neutrino telescope there? Because you need to have a very good medium. So we deployed so-called PATHFINDER missions, smaller things of what you've seen sort of on IceCube. So these are only 150 meters high, but they have, I'll show you a little bit more. So they're essentially also these photosensitive devices, and we also have light emitters in there in order to understand the optical properties. So you can see here, these are the experts from ONC. Here you can see, that looks almost a little bit IceCube-like. It's not a surprise because literally everybody who was working on P1 has worked previously on IceCube. So it's obviously, why don't we try something we know already how to build and put them down there and see what we can learn. And here you can see how this is operated. So this is now almost 3 kilometers deep in the water. And of course, there's no divers who go down. It's these remote-operated vehicles, these little dive robots, which go down and connect everything down there in terms of power and data transfer. So what have we learned? The first important thing over these 2 years here, we have a lifetime. This means the detector was operational almost all of the time. And this is really, really important for astrophysics. So the LHC, we always know exactly when the LHC is operational. So the experiments know exactly when they have to take data. So if you're good, you don't miss anything. It's hard enough, this business. But here it's even harder. You never know when something blows up in the universe. The universe doesn't give you a hint beforehand. So if you're only 50% of your time taking data, you have a serious problem because you're probably likely to miss something. So IceCube has 99% operational lifetime. You can see here we reach almost the same. And this is less the detectors. This is how good ONC is. So this was really important to understand. can they actually operate on a duty cycle to make this happen, that we are almost all the time operational, so we don't miss anything in the universe if something blows up. The second thing is the water good? And yes, it is good. So I don't want to discuss this plot here too much. Obviously, you can see the wavelength of the color spectrum we usually can see. And here's something we call attenuation length. So you can imagine the larger this is, the longer the photons survive in the water, so the better it is, because the clearer the water the clearer the water. So Cascadia Basin has these black curves, so this is pretty good. The way we do this, we have light emitters. We flash here quite bright light flashes, and we try to detect this at different distances. And you can obviously quite easily understand the more light you detect at certain distances, the better your optical properties. So this is how we could determine the optical properties with these, let's say, PATHFINDER missions down there. We also understood quite a few other things, but these are the main parts. So what have we learned? So we have learned from these PATHFINDER missions that the Cascadia Basin, which is this site from ONC, is actually suitable to build, that we can build a neutrino telescope. We also have learned that it's actually really quite interesting what we can do in terms of interdisciplinarity. So what we can bring to the study of oceanography, microbiology, or also climate change related studies. Because Canada, also in the Pacific in general, there's no instruments of anywhere that size who could sample and understand the ocean with such an extent. So you have to imagine these are, in the end, kilometer-long strings, an array of a cubic kilometer. Nobody's usually mad enough to build ocean sensors to an extent of this size. So here you see, for example, these bioluminescents. So these are pyrosomes which emit light. So we had cameras down there, so you can see the emission of them. You can also study them. They're very hard to study. People actually haven't studied them much at all. What you see here is a simulation. All of these little dots are these kind of organisms. When they are disturbed, they emit light. If they're undisturbed, they just float through the ocean and do nothing. This little black dot here is essentially our optical module. So if they flow in the water current and they get disturbed, then they get red, then they emit light. So this is a simulation of two populations of possible pyrosomes. And you can see these are photons, so light which is emitted over time. So you can see the kind of different, what you would expect, what they emit. So we put a device down there which is able to do exactly that. And this is now not simulation, this is data. So this is not a detailed analysis which is happening at the same time, but you can see already qualitatively they look very similar. So you have the power to actually understand what is down there in 2.5, 3 kilometers deep in the ocean. You can understand these organisms. So there's a huge power what we can do with these detectors, which is not physics, which is very interesting to the community. Okay, so as a very last few slides, where are we and what are the next steps to actually try to make this a reality? Because these experiments, as you've seen, cubic kilometer is quite big, also costs quite a bit of money, and you don't build this for literally in 1 week. So what we've done is what we call phase 1, which is our PATHFINDER missions, which is we had a vision, it's always good, and then we qualified the site. So we actually figured out this is possible. So we can do this. So now we are in phase 2, which we would call pilot phase. So this is our concept now. We are conceptually designing and building the detector the way we want to have it. Because IceCube is a technology which is more than 20 years old. The other neutrino telescopes are already technology which is more than 10 years old, what they're trying. So as you know with your smartphone how fast they change, this is how quickly technology changes. And you can build new object or new detectors which are significantly more capable and have significantly better properties in principle. Always has to be seen. So this is the phase where we're currently in. So we're trying to design the first prototype lines and also deploy them. So to give you a size scale, this is what I showed you, these two little 110, 150 meter long strings. We deployed a second prototype, which was already 400, 450 meters long, and this is what we actually want to put down in, let's say, 1.5 years. This is a blueprint of how we envision P1 to look like, which is a kilometer-long string. So the whole mooring line is like almost 1.3 kilometers long. These are the sensors we are building. So you can see they look somewhat similar still, but also quite different. So now we don't have one big, what we call light sensor, which is photomultiplier tube anymore. as you know, pixelation, as in all your smartphone cameras, the more pixels, the more information you can get. So we are also pixelating this with a lot of small photo devices, because then you can learn significantly more and suppress your background significantly better. All right, so this is the timeline, what we're trying. This is the proof of concept, which is currently in development. In 2024, we want to deploy that. This is what we currently are working towards. So this is a first cluster of a few strings, which we want to operate together. And this is what we have to prove to the world, to everybody, that we can do this, that the detector works, that you can do science with that. This size is not good enough to do the same astrophysical studies what IceCube is currently doing, because you need to grow in size. So this would be the last phase, which of course would be then discoveries, and you need also a lot of international collaborators to build such a cubic kilometer size detector. So what we're trying to build right now would be, in this image, one of these clusters of these, which we try to operate. All right, so as I said, I hope you learned what a neutrino is, for those who haven't known that before. I also hope that you got an idea why neutrinos are special. As I said before, they're also special in many other ways, but special for astrophysics. Then how we can detect them, especially these high-energy neutrinos in these neutrino telescopes. And I hope you also understood why BC is so interesting for them, that we want to build such a detector right here. It's because of this partnership of something which already is existent. So the seed has been found. Now we just have to actually see if we can do it. All right, so neutrino astronomy, I think, came a long way. It has started now with IceCube. It's a wonderful experiment. It's really exciting, and it's skimming the threshold of seeing the really exciting things. So we know the discoveries are out there, but it's just not big enough to make these discoveries. I also hope you could see that the neutrinos are the high-energy messenger of the universe. So there's literally 20% of terra incognita, where we have not seen it all. Would be exciting to understand what we can see there. But we need more neutrinos to study them and understand what the universe is telling us. And it would be very fun to do this in BC and not somewhere else. And the last thing is, neutrinos are never boring. In the last 50, 60 years of particle physics, neutrinos have probably yielded the biggest surprises to all of us. So why not? Maybe there are more surprises. So these are just some of us in a recent meeting who are trying to build this. And thank you for your attention.